Good evening, everyone. My name is Lishoy Frances. This is Matt, my colleague. We are really excited to be here, to be part of the Cyber Cluster, Cyber Security Cluster. We are bringing our expertise and knowledge in mobile application security. A bit about the company. So we are called Consult Hyperion. So it's a boutique consultancy based in Guildford. We have offices in the US, and then we have associates and consultants spread out across the globe. So it was founded around 30 years ago. So we did work in, we designed the open loop system for TFL, for instance, one of the notable projects. We're advising governments and central banks on CBDC these days. And some of my colleagues, they wrote the original specs for the payment schemes, EMV. And then we are continuing to support them, support the schemes to maintain those specs and also meet their certification requirements on EMV level 1, level 2, for instance. We also offer security testing, which is the mobile app penetration testing practice. So I'm managing it. I'm managing a team of ethical hackers and security consultants who has got strong background in security research, compiler optimization, and then understand the ins and outs of the mobile operating systems, for instance. It's a small team, very focused. So we have been testing since over about 10 years now. So we have looked at apps across various sectors, like mobile apps, mobile banking, in payments, including wallets, apps used in electronic voting, trialed across the world, and then also in the US, in rewards, and then also retail sector. So here in this talk, I'm not pinpointing a certain client, a particular vulnerability or particular product. So I'd like to share our observations from our testing practice, and then also touch upon some of the common defects that we find. And then Matt will show a cool demo of a complicated vulnerability. So, with our pen testing, so we do two approaches. One is a white box, the other is black box. So with white box, we review the full design, the architecture. We understand the full source code. We do a full review of the source code. We look for defects related to programming languages, for instance. So we understand what data types are suitable for certain sensitive data, for instance. So for example, someone might use, we have seen in practice that developers are not fully aware of the data types, what to use and in what context. So they might use the immutable object in Android, for instance, which means for let's say sensitive data, for instance, like a payment card data or personal information. And then those objects are left in memory. So anytime those objects are called, a copy is left in the memory. And then let's say you manage to crash the app, that data is readily available in the memory. So we check such aspects, including business logic. We also, we use an approach of, we do manual checks as well as we do automated scan of the code, looking for certain patterns. And then we do a full introspection of the app. We do a full runtime testing. So we check the workflow end to end. So we look at how data is handled in REST, in transit, how it's visible in the memory, for instance, as I mentioned before. And then we also look at how the crypto is deployed, so whether you have the right safe and sound algorithm being used, and then are there any known weaknesses around it. We also check the entropy of the identifiers and the keys used. And then we also look at, I mean, these are all activities. I'm not probably going through each item. So we also look at SDKs and libraries that are deployed in the code. Often there are known vulnerabilities in those third-party code, for instance. And then in the black box approach, we can decompile the APK or the IPA, disassemble the IPA. We can do a full introspection again. We understand code obfuscation. So in the past, we have seen some of our clients deploying code obfuscation using only the default config, for instance. So in one instance, we found the bit code not properly randomized when the build was made. And then given time, you could reverse and deobfuscate. We also look at how what measures are there in place for tamper detection, and then also for integrity protection. And then the mobile app testing doesn't end there, so it goes a step beyond. So it goes beyond to the CDNs and then to the API services in the backend. And then often we see app will be a front end to those services, and then if you can get untrusted code to the downstream, you can make an impact down the systems further. So methodology is very bespoke. So it's models based on conforming to the OWASP security standard, and also the guidance on web apps. So what we have seen is actually the app providers are now adding in, on one side, adding in lots of features. The features are getting cramped. The apps are getting bloated, if I may say. And on the other hand, there's some maturity we see on the security mechanisms. So some of those security mechanisms may be developed based on the platform provided frameworks, or it can be completely bespoke. So for instance, data stores. You might use shared preferences in Android. But then you have a new Jetpack which will add encrypted, you can use encryption there as encrypted shared preferences. But some providers are going a step further. They're looking at creating bespoke containers. So there are added layers in what we have seen coming up from what we have seen in the past. And then for TLS, for example, for the transport security, you have TLS commonly deployed, but some providers may use a bespoke secure channel. So in demo, Matt will demonstrate why it might be needed. And then providers are also deploying advanced authentication mechanisms. So they're not just relying on Face ID, biometric-based Face ID or Touch ID. They're adding multi-factor authentication. So it can be SMS OTP-based, but then you might argue it's not very safe. They are deploying push notification-based challenges. Now we also see ID verification based on government-issued documents, for instance. So they add a lot of complexity to the authentication mechanisms that we have seen in the past. So if I take an analogy of Old English castle, so that's not a castle, as you can see. That's a modern version of it, probably, somewhere in the US. So you build layers around it. So let's say you have a castle, you have a moat around it, you have different layers of security, footmen, doorman. You have drawbridge, giving one access to the castle, for instance. So if I take that analogy, so the apps, these days the providers are adding a lot of layers of security, but then they are probably, not focused on hardening each layer. So those layers are very important. You have to harden each and every security layer. So because the apps are not just communicating using a gateway to one particular gateway, a third-party code in your app might be talking to an external server or many external servers. And then there are many entry points, for instance. So you might use app links or deep links to invoke your app from a browser session, for instance. So the complexity has increased. So the interaction of the app to the external world, to the other components are manifold. So that's that, use an example of as a network topology of the interactions there. But that actually means the interactions are not linear, or it's not just in a simplified manner. So the app providers often overlook, especially with the third-party code. So on the other side, the software composition is becoming more complex of the apps. So the features and the security mechanisms which I mentioned, touched upon before, might be implemented using the native code of Android or iOS, or it can be implemented in native C or C++ code. And then we are increasingly seeing the use of web views. So web views, if you're not familiar, so they are mini browsers which can render web code like JavaScript and HTML. And then you can deploy some features or some applications which are available online in a fast manner into your releases, for instance. So you have kind of apps within the apps. So you have a new workflow within the normal app. So you won't see it as a user. You won't notice the difference as a user. But then those web views are becoming attractive target for the attackers. Why? Because some of the code loaded in the web view, they may not originate from a trusted source. So they might originate from a third-party server, for instance. And then not many app providers are reviewing that code. So you're looking at an attacker using exploiting WebView-based code, and then getting deeper into the backend, let's say to some advisor system where some code or some data has been presented. And then those advisor systems, for instance, like they might be using some legacy software. And then now you're giving a new attack vector using the WebView, for instance, if you're not thoroughly checking it. So some of the code can be compiled in, so which means you can you review it, and then you're sure that what code exactly that is, whether it's doing the expected goal or not. So we have seen that in a composite view of the apps. So the apps are not just being written in iOS or Android. They are using several different kind of frameworks, web views, and then also uses APIs to access several backend services. And then, as I mentioned, the third-party code. So we see a lot of dependencies. So there are like hundreds of them. So this can be fully open source. It can be, let's say, in-house developed, or it can be third-party developed. So the dependencies needs to be checked, because those dependencies may have some known vulnerabilities, and then attacker may combine one or more vulnerability and then make an exploit. So this is a kind of after effect of extreme agile environment, if I may say. So from the time of ideation to the release, it's becoming shorter and shorter. And then developers are usually overlooking the use of these dependencies. They're probably liberally using it without understanding the potential risks. You should check where your dependencies are added in. You should check the build pipeline and then the release pipeline, for instance, because there might be many issues out there which you're not aware of. So it's not always in the app code. I gave you a hint. So it can be in the service in the background, for instance. So what you see in the screen is a REST API which accepts HTTP, JSON payload over HTTP. And then you send a malformed payload. It triggered a HTTP 500 internal server error. It not only stopped that service, but it gave a very interesting error. So it just released, it returned the information of the framework used. Here is a Spring framework, some of you are probably familiar, because of a type mismatch. So here, this request, in this request you can see the parameter 1. So it has some additional data there, some special characters. It triggered that result. So from an app developer perspective, he has done all input validation check, data validation check on the client side, on the app side. But let's say as an attacker, and this API actually uses implicit authentication using the session ID, for instance. So as an attacker, you intercept that request, mounting a man in the middle on the communication channel. You can inject, you understand what APIs go back and forth, what's being called, and you can manipulate the payload and then try to get some errors, try to get some info from the backend. So either maybe crash the service or maybe leak some sensitive information. So in some cases we have seen even internal network details, for instance. So use a dictionary of malformed requests, payloads, and then create malformed requests, and then bombard the service, and then get some information back. So this is a big issue. So probably it's not being focused because everybody is looking at the app code, but then they are not looking at what APIs are being consumed and then how those APIs can be exploited. So again, I said, so as I mentioned, these are verbose errors. And once you understand the framework as an attacker, what I will do, I'll go to one of the vulnerability data source, like a NIST, NBD, or SV, or Meta, CWE, and then I'll look for some known vulnerability there. And then there you go. So you have, so that's a list of vulnerabilities present on Spring Framework. And then you try to think, then you understand what's known, and then how we can exploit that, and then take it from there. So from a developer point of view, that error might look very benign. Maybe you mark it as a low severity or just informational in some cases, but then it will have some real impact at one time or the other. So the best practice would be to return only generic errors, for instance. And then you have to test your APIs really thoroughly. And then, of course, you monitor for any known vulnerabilities in the frameworks that you use, for instance. So as I mentioned, the communication channel, this is really key. It's not really easy to secure a communication channel between a mobile app and the backend. or backend server, as compared with a browser and a backend server, for instance. So again, as I mentioned, apps are working in a client-server model. So you deploy TLS. You can have two-way authentication or one-way authentication. So that's the TLS handshake. So you readily get three aspects. So authentication, confidentiality, and integrity, and create a secure channel. And you're deployed, you think you're secure, but probably you're not. So one of the aspects for TLS is actually you're getting the authentication from, you're getting some signal, some assurance of authentication. But then how can you really trust that particular server? You can't. You just can't, because it could be anybody in the middle on the channel. So there are, it's a known technique used at certificate pin. So you pin the certificate of that end node, and then you, when you establish the connection, you check, validate that certificate and see if it's the right certificate, that's what's expected, that's presented in the channel. And then you can do a lot of checks. So you can check that certificate through the whole hierarchy up to the root certificate. You can create a chain of trust. But then there are many issues there, because just by implementing a certificate pin doesn't solve the man-in-the-middle issue in the channel. So it could be you might trick, and as an attacker, I might trick a user to install a self-signed certificate, which is trusted by the device, and then game over. Or it could be a rogue CA, for instance. It can happen. It has happened in the past. One aspect we see is actually, so the certificate pinning information and then the required information to talk to the backend is stored, to establish the TLS with the backend, is stored in a separate file, let's say in a network config file, for instance, within the belt. And then that code, or the validation and also the data is not adequately protected, for instance. So there is no, let's say, tamper, there's probably a rudimentary tamper detection. There might be, there's probably no integrity protection. There's no code obfuscation, anything deployed. So that logic of doing the pin check is fully vulnerable at this stage. So what happens if an attacker decompiles your app, substitute that network config file, and then, let's say, make a new build, resign it, and then release it over a phishing campaign, for instance. So the users might think, oh, this is the real app. Maybe this is an update to my banking app. I will release it, I will download it, I will install it. And then there you go, your basic authentication onwards, all sensitive information is compromised from that stage onwards. So I'll hand over to Matt, who will demonstrate the aspects which I discussed.
Thank you, Lishoy. Right, so let's first explain the setup. I can find where the cursor is. Here we are. Okay. So we have an application on this Android device. It's a technical demo we put together several years ago now to show the feasibility of using what was then new technology called NFC to make an Android phone act as a terminal. So this is demonstrating host terminal emulation rather than HCE, which is your phone acting as a card. Okay, so here's our app, and we shall put in some money, and we can then take a contactless payment with it. And it goes online, and authorizes the transaction, and everything works, okay? So I ought to explain this app is not, this is just a technical demo app to show the feasibility of gathering card transaction data from a mobile phone. It hasn't been hardened in any sense, so I'm going to be showing why that's not, why that's not a good idea. And the card I'm using is not a real card. So you're going to see some card numbers, but they're not real card numbers. Okay? But this would work with real cards too. The app is communicating to a back-end service to do the authorization, and in that channel it's sending the card number. And obviously that's going to be a thing that any attacker would like to get their hands on. So the first thing we're going to show is how vulnerable this would be if you hadn't done certificate pinning. And this app at the moment doesn't have certificate pinning in it. To do that, what I've done, on the phone, set up, it's working through a proxy, which is through my own sort of hotspot on my phone that I control. So as an attacker, you could set up your own hotspot and somehow through social engineering convince your victim to connect to that hotspot, and perhaps convince them to, well, you've got to connect as a proxy and therefore trust this certificate. And therefore, as an attacker, you can intercept all that traffic and gather the information. And that's exactly what's happened just in that last transaction. And down here, you can see the card number. Okay? So all I've done is convince the user of the app to connect to a proxy server on the Wi-Fi hotspot I control and install the certificate required to do that connection. So as Lishoy said, well, how would you protect against that? Well, you'd use this thing called certificate pinning. And as I think he said, what that does is you tell your application when you set up a TLS connection, ensure that the certificates you get back include certificates with a certain public key within the certificate chain. So I have a version of the app which does this. I'll just delete this version. We'll install the updated, even more secure version. There we are. Let's work this time. There we are. And we get a certificate verification error just being put on the screen because the certificate pin process threw up that error. Okay. So far, so good. So as an attacker, what could you do about that? Well, one thing you could do is, as Lishoy pointed out earlier, you could decompile the app, make some changes to it and remove that certificate pinning, and convince your victim to reinstall this new improved app on their phone because it gives you better service, okay? So we're going to try and do that live. Okay, so what I'm going to try and do is decompile that code. Right, so what this is doing is decompiling that app with our certificate pin in it into a folder structure. Okay. So here's our folder structure with all the code and files. But the one we're interested in is down in our res XML file, and it's this network security config. There's our pinning information. So now what we're going to do is just delete that. So there's no pinning involved now. Save the file. And now we're going to rebuild the APK. So what that's doing is going through all that previously decompiled code and the modified network config and rebuilding it. So hopefully now we'll get a new APK. Yeah, there it is in the bottom. Output removed. Pinning. And the last step we need to do is now sign that. But we can obviously not sign it with the original key, because as an attacker we probably wouldn't have that, but we'll sign it with our own key. Okay. So now that we've created that APK, we've delivered it to our victim, who now thinks it's, you know, new improved app. So we instruct them to uninstall the old one. And reinstall. Okay. Okay, do our transaction again, and hopefully we shouldn't get that nasty certificate error anymore because we've removed the certificate pin. Correct, and it's done. And once again, you can see card number. Okay. So that's it. Very simple demo of TLS security and the sort of things an attacker can do to get around some of the defences you put in. Obviously this was not built or designed with security in mind, this app, because it was a technical demonstrator. A real terminal implemented on a off-the-shelf device, I would have expected a second secure channel in there that encrypts the data as it's sent over that TLS connection, that is initiated on login with a session, a separate session key each time, with that key being changed and diversified for each transaction. I would expect the app to include tamper detection to detect that, hey, this isn't the right signature for the app, you know. I would expect obfuscation, so you can't see once you decompile the code exactly what's going on, to identify the weak points and to identify what you could change to change the pin. All sorts of things to help boost that, your castle's defences, and to police them. Thank you very much.